Welcome to the Introduction to Vblock Systems Storage section of the Vblock Foundations course. Recall that Vblock systems are composed of compute, network, storage, virtualization, and management technologies. In the previous sections of this training, you learned about the Vblock systems, compute, and network. Now you'll learn about the basics of storage technology. The objectives for this section are listed on this page. Upon completion of this training, you'll be able to explain the function of the storage within a Vblock system, distinguish between file-level and block-level storage, list and explain the purpose of each of the components of the Vblock system storage, and describe the connectivity of Vblock system storage for block-level storage configuration and unified storage configuration. In this section, you'll learn about the basics of storage technology, as well as the function of storage in a Vblock system. Let's start with some storage industry-related facts. International Data Corporation, or IDC, is a market research firm specializing in information technology. Over the years, the IDC has completed several studies on the amount of data being created in the world. They call the amount of data generated each year the digital universe. They have measured the digital universe at 130 exabytes in year 2005. In the year 2012, 1,227 exabytes of data were created. To put that in perspective, 1 gigabyte equals more than 1 billion bytes. 1 exabyte equals 1 billion gigabytes. Now here's a question for you. Given the number of exabytes generated in 2005 and 2012, what do you think the projected size of the digital universe is for the year 2020? Currently, the IDC predicts that in the year 2020, the amount of new data that will be generated that year will be over 40,000 exabytes. That's 40 trillion gigabytes of data, or more than 5,200 gigabytes for every man, woman, and child alive. With that amount of new data generated every year, imagine the amount of computing power and storage capacity that will be needed to create, and manage, and save it.
Storage is a core component of computers which provides a safe place where digital files and block data are stored. Unlike computer memory or RAM, which loses its contents when power to the device is turned off, information and programs saved in computer storage are retained even when powered down. There are different types of media used for computer storage. These include magnetic media, like hard disk drives and floppy disks, solid-state media, such as thumb drives and flash drives, also referred to as solid-state drives or SSDs, optical media, like CDs or DVDs. Vblock systems do not use optical media as a storage option, and you won't learn more about those in this training. Typical desktop and laptop computers contain one or more of these devices. These are usually used solely by the user or owner of that computer. Storage arrays, like those found in Vblock systems, can contain from just a few storage drives up to thousands. They can be accessed over a network and are shared by many users. The storage drive options for a Vblock system, which you'll learn more about in the next few slides, includes both disk drives and flash drives. In computers today, disk drives are the most common storage medium for storing and accessing data. They contain a number of rigid disks that are coated with a material that can be magnetized. Data is written to and read from these using devices called heads, which float a small distance from the disk, separated from the surface by a cushion of air created by the spinning disk. Disks have a large capacity and support rapid access to random data locations on a disk. This means the data can be written or retrieved quickly for a large number of simultaneous users or applications. Disk drives have many moving parts which limit performance and over time wear out and eventually fail. Disk rotation speed and the head motion speed influence drives performance in terms of data transfer rate and latency. Disk technologies found in Vblock systems includes fiber channel, SATA, and SAS drives. Fiber channel drives have some of the highest available rotation speeds and therefore also have among the highest sustained data transfer rates. SATA stands for Serial Advanced Technology Attachment. These generally have the slowest rotation speeds of drives found in Vblock systems. SAS, or Serial Attached SCSI, come in a variety of physical sizes and with a variety of rotational speeds to meet the varying performance requirements. A slower version of SAS drive that is similar to a SATA drive is commonly referred to as a near-line SAS drive. Flash drives, or solid-state drives, use semiconductor media. They have become a good alternative to disk drives in certain situations that require high performance when speed and particularly latency is important. Because SSDs have no moving parts, there is virtually no latency for random data access. In addition, the operation of a flash drive requires less power and generates less heat than a spinning disk. Most Vblock systems contain some solid-state drives, referred to as enterprise flash drives, or EFDs. These drives are packaged with a size, shape, and connectivity similar to spinning disk drives, so that they can be mounted into the same enclosures. Although solid-state drives have no moving parts to wear out, the circuits that store information each have a maximum number of times that they can be rewritten. Therefore, flash drives can eventually wear out from heavy use. A common computer, like a desktop, laptop, or tablet, typically contains at least one disk drive or solid-state drive. The compute portion of a Vblock typically does not have any integrated storage, but instead connects to a number of drives grouped together in an enclosure called a disk array. The advantages of a storage array includes the ability of multiple servers to share storage simultaneously to increase efficiency. It also can provide more storage to the operating systems and applications than any one physical drive can. Additionally, the storage processors, which we will discuss later, increases the overall performance beyond just a bunch of disks connected to a computer. Generally speaking, there are three methods of attaching computers to storage. Two are standard options within a Vblock system. With direct attached storage, or DAS, storage devices are attached directly to a single computer, which we call a host. The sharing of these devices by more than one computer or host is generally not practical. Only the host computer has direct access to DAS storage drives. Data sharing with other computers must be coordinated through the host. Other non-host computers typically cannot access the DAS drives directly. This method of attachment is not available for the portion of Vblock systems that uses virtualization, but is an option for bare metal installs. In network-attached storage, or NAS, hosts attach to storage through an organization's network, which typically serves many purposes other than access to storage. Because of this, multiple computers can directly access NAS drives and share storage space at the same time. A storage area network, or SAN, is a dedicated network that is used exclusively for providing connectivity between a computer and storage. Network-attached storage is a concept of shared storage on a local area network, or LAN, and it leverages the benefits of a network file server and network file storage. The native protocol for sharing files in a Unix and Linux operating environment is the Network File System, or NFS, network protocol. The Common Internet File System, or CIFS, network protocol is native to Microsoft Windows environments. Additionally, the File Transfer Protocol, or FTP, is available in most environments. NAS brings platform independence with reasonably good performance to a network. NAS provides security and performs all file and storage services through standard network protocols. Although NAS trades some performance for manageability and simplicity, it is by no means a lazy technology. Gigabit Ethernet and 10 gigabit Ethernet allows NAS to scale to high performance, making it possible to support a myriad of clients through a single interface. Many NAS devices support multiple interfaces and can support multiple networks at the same time. A storage area network is a network that is dedicated to communications between hosts and storage devices. It allows multiple servers, even if of different types and platforms, to access the same storage array ports. SANs leverage high-performance protocols such as Fibre Channel and efficiently utilize available bandwidth for servers to process large numbers of transactions or operations concurrently. A SAN network provides virtual, dedicated connections between servers and storage.
In this section, you'll learn some basic concepts on storage technology that are important to understand before we discuss storage connectivity in a Vblock system.
Block-level storage is required on all Vblock systems. Remember that Vblock system compute servers do not contain storage. Their operating systems are loaded on storage drives, and the servers boot from block-level storage. Block-level storage is typically accessed over SAN using Fibre Channel Protocol and its SCSI subprotocol. However, as you learned in the Vblock System Network section of this training, block-level storage can be used over Ethernet using the IP protocol and the iSCSI subprotocol. You'll see later that one Vblock system platform boots from block-level storage using the iSCSI protocol with no SAN. All other models have a SAN. In block-level storage architecture, storage is presented to the compute host as logical units, or LUNs. You'll learn more about LUNs in a moment. Block-level storage is typically accessed through a SAN using the Fibre Channel Protocol. Storage is assigned to a specific host, a physical or virtual server, and unless clustered, only that host can access the storage directly. File-level storage is an option available to Vblock system customers. File-level storage uses file-sharing protocols that have the capability of sharing the same directories and files using both CIFS and NFS protocols simultaneously. File-level storage is presented to the host through a LAN or IP network as a file system of folders and files. It requires a file server to manage how data and files are stored and retrieved. It also manages which hosts can access the data directly. Unlike block-level storage, which limits direct access to a host it is assigned to, file-level storage can grant access capabilities to multiple concurrent hosts. File-level storage is easy to set up and use. Block-level storage is a requirement of all Vblock systems, and some customers choose systems with exclusively block-level storage. Vblock systems are not available with exclusively file-level storage. Customers who need file-level storage purchase systems with a unified storage configuration that has both block and file-level storage capabilities. In a block-level storage implementation, a LUN is the logical unit which is presented to a host for its storage needs. A LUN is an abstraction of a disk drive and is conceptually a set of consecutive blocks of storage. A LUN is not a physical storage drive. is a virtual storage drive that is abstracted from one or more physical storage drives. While it doesn't exist physically, it has all of the same characteristics of a physical storage drive. Hosts generally don't recognize the difference between a physical drive and a LUN. A LUN presented to a host is viewed by the host as a physical disk. Depending on the needs of an application, a single physical storage drive can be divided up into several LUNs, all of which can be presented to a host computer as a distinct storage drive. Or if needed, a single LUN can consist of the storage capacity of several physical storage drives or parts of several drives. A host views a LUN as a distinct storage drive, even when a single drive is segmented out into several LUNs. The size of a LUN is configurable within the maximum and minimum size boundaries supported by the storage array. When a LUN is created and presented to a host, the process is referred to as provisioning. Using tiered storage helps organizations to both manage storage costs and efficiency. A couple of factors contribute to this. First, not all data is equal. Some data is accessed and changed nearly continuously, while some other data may not be touched for months or even years. It would make sense that data used frequently be easier and faster to access than data that is hardly ever accessed. Second, as you learned earlier, not all storage drives are created equal. Some are extremely fast but expensive, while others are inexpensive but slower. Tiered storage is a strategy of matching the rate at which data is accessed to a storage drive type. Think about it. If all of a company's data is saved on flash drives, it would all be accessible extremely quickly, but it would be expensive. If thousands of flash drives are needed to save all of the company's data, the cost of the storage hardware could become prohibitive. It is smart to put some data that is accessed frequently on flash drives, but what about the data that is used infrequently? In this case, slower, less expensive drives will reliably secure the data and save money. Tiered storage allows you to match drive speed and cost to data use. For example, if you need an array with 100 drives, you can buy a mixture of solid-state flash drives, SAS drives, and nearline SAS drives. Remember that flash drives are the fastest, nearline SAS drives are the slowest, and SAS drives are in between. In a tiered storage configuration, you would put the data that you access most frequently on the fastest drives, the data that you use least on the slowest drives, and data used in between can be stored on the SAS drives. As a result, data access requirements such as storage drive speed and cost are controlled by using less expensive drives where appropriate. It should be noted that EMC storage arrays have the capability of automatically moving data between tiers using a technology called Fully Automated Storage Tiering, or FAST. It periodically assesses the frequency at which the data is accessed and automatically and appropriately distributes data across the different drive types. We'll talk more about this later. Thin provisioning is a method of dealing with common problems with traditional storage allocation. The problem is that many systems never use the amount of storage that they are allocated. In a traditional data center, users project the amount of physical storage that their applications need. Users will often overestimate the amount of storage that is needed because in traditional organizations, adding storage after the fact requires purchasing, installing, and configuring new hardware. Let's look at an example. For this scenario, we'll assume that we have a storage array with a capacity of 2 terabytes. We have 3 users requesting storage for their projects. The first asks for 400 gigabytes, the second 500 gigabytes, and the third 800 gigabytes. As a result, we create 3 LUNs and allocate them as ordered. After the applications have been running for some time, we examine the storage utilization of each of these applications and find that each application is using far less storage than anticipated. The result is that there is more unused capacity than there is actually used. The unused capacity is a resource underutilized and costing the organization money. Allocating storage virtually creates a different reality. Here, the allocation for storage for the same 3 applications will start with a 1 terabyte disk instead of 2 terabytes. The storage requirements are defined for the application, but not allocated until the application produces data to use that storage. The difference is that the storage isn't set aside for use by only those 3 applications. Instead, what is provided is a promise that the requested amount of storage will be there when and if the application needs it. As a result, when applications use less storage than what was requested, which happens often, there is less unused allocated storage. Instead, smaller disks can be utilized, which reduces purchase and operating expenses. When more logical capacity is provisioned than physically exists, it is called overallocated or oversubscribed. Moving data between tiers using a technology called Fully Automated Storage Tiering, or FAST. It periodically assesses the frequency at which the data is accessed and automatically and appropriately distributes data across the different drive types. We'll talk more about this later. Thin provisioning is a method of dealing with common problems with traditional storage allocation. The problem is that many systems never use the amount of storage that they are allocated. In a traditional data center, users project the amount of physical storage that their applications need. Users will often overestimate the amount of storage that is needed because in traditional organizations, adding storage after the fact requires purchasing, installing, and configuring new hardware. Let's look at an example. For this scenario, we'll assume that we have a storage array with a capacity of 2 terabytes. We have 3 users requesting storage for their projects. The first asks for 400 gigabytes, the second 500 gigabytes, and the third 800 gigabytes. As a result, we create 3 LUNs and allocate them as ordered. After the applications have been running for some time, we examine the storage utilization of each of these applications and find that each application is using far less storage than anticipated. The result is that there is more unused capacity than there is actually used. The unused capacity is a resource underutilized and costing the organization money. Allocating storage virtually creates a different reality. Here, the allocation for storage for the same 3 applications will start with a 1 terabyte disk instead of 2 terabytes. The storage requirements are defined for the application, but not allocated until the application produces data to use that storage. The difference is that the storage isn't set aside for use by only those 3 applications. Instead, what is provided is a promise that the requested amount of storage will be there when and if the application needs it. As a result, when applications use less storage than what was requested, which happens often, there is less unused allocated storage. Instead, smaller disks can be utilized, which reduces purchase and operating expenses. When more logical capacity is provisioned than physically exists, it is called overallocated or oversubscribed. The benefits of thin provisioning are clear. Cost efficiency increases when you decrease unused storage capacity. Capacity is only used for actual data stored, not for empty allocated space. Over-provisioning, or having less storage than is requested, is allowed. However, when oversubscribed, you must carefully monitor available storage capacity so that you can always deliver on the promise of storage capacity when the applications need it. Failing to have sufficient capacity when an application needs it can result in data being lost. Redundant Array of Independent Disks, or RAID, provides data protection and can speed the process of reading and writing data to storage drives. When you consider that there can be hundreds and even thousands of drives in an array, the chances that some drives may fail is real. When storage drives fail, the data stored in them can be lost. RAID methods can ensure that when a drive fails, the data is not lost. There are several standard methods of RAID configuration. We're going to talk about 3 methods here before we learn how they are implemented in Vblock systems. The 3 methods are mirroring, striping, and parity. Mirroring is simply saving the same data to 2 distinct drives. With this method, there is always a duplicate copy of the data. In the event that a drive fails, a copy exists on the second drive. Mirroring improves read performance because read requests are serviced by both disks. However, write performance is slightly slower than a single drive because data needs to be written twice. Mirroring is referred to as RAID 1. Striping can increase read and write speeds because portions of the data are simultaneously read from and written to multiple drives at the same time. The logical unit of data that is distributed across multiple physical drives is called a stripe. Because more input and output paths are used, the data transfer rate is effectively multiplied when writing data to multiple drives at the same time. Striping is known as RAID 0, and it does not provide any data protection, because if one drive fails, all of the data on all of the other drives is now incomplete and not usable. Parity is a method of protecting striped data from disk failures with less cost than mirroring. A portion of each stripe is dedicated to storing information calculated from the rest of the stripe, so that if a drive fails, the missing data can be calculated and recreated. The 2 parity RAID types used in Vblock systems are RAID 5, where one portion of each stripe is dedicated to parity, and RAID 6, where 2 equal portions contain complementary parity, so that the recreation can be performed even if 2 drives fail before the recreation completes. RAID 5 and RAID 6 sacrifice less storage space than RAID 1 protection, but parity RAID increases the workload on the storage processors, which must calculate the parity in addition to performing the other array management tasks. This slide illustrates the relative overhead of the various RAID types. On Vblock systems, there are specific tested and approved RAID group sizes. It should be noted that with RAID 5 and with RAID 6, the drive that contains the parity information varies from stripe to stripe to reduce the likelihood that one drive will become overused. The distribution of the parity across the various drives is handled automatically by the storage processors and is completely transparent to the computers connecting to the storage.
Now that you have a basic understanding of the purpose of Vblock System's storage layer and an understanding of some basic storage principles, let's discuss the Vblock System components.
On a high level, the basic components of the Vblock system storage includes the following: storage processors, data movers, and storage enclosures that contain storage drives and/or storage processors. Vblock systems come with EMC storage arrays. The Symmetrix Vmax family is the most powerful. The VNX storage family has enterprise performance and reliability at a more affordable price, and the VNXE is frequently the best fit for remote offices or branch offices, additionally for small projects. We'll learn more about these later. Storage processors are physically situated between host computers and physical storage drives. They can be looked at as having 3 logical parts: a front end, cache, and a back end. The front end provides ports for connectivity to the network, and the back end provides ports to connect to the individual disk arrays. The cache is memory, where data is temporarily saved when moving from the back end to the front end, and also before it is written to the storage drives. A significant bottleneck in the process of saving data to storage is the time it takes to physically write or save data to storage drives. To help alleviate this, when the storage processors receive data, it is written first to cache. Because cache is RAM, the time it takes to write data to cache is much less than writing to storage drives. Think of cache as a staging area where data coming into the array is saved quickly to reduce traffic jams of data waiting to be saved to the storage drives. Once data is saved to cache, the applications and operating systems can move on to the next task, and the storage processors can move the data from cache to storage drives as a background process. Cache significantly improves storage write performance, and it can also improve data retrieval performance using a technique called prefetching. When a storage processor is retrieving a large amount of data sequentially, it can predict what data will be needed next and pull it into cache. Data is held in cache to quickly respond to read requests. If the prefetched data is never requested, the storage processor will eventually delete it from the cache. This process of prefetch can speed the retrieval of information from the storage drives. In Vblock systems, file servers used for file-level storage are contained in the EMC storage and usually referred to as data movers or X-blades. These file servers only provide file-level storage. Therefore, they are not needed in systems where only block-level storage is used. Remember that file-level storage is only available in Vblock systems with unified storage, so file servers will be present when unified storage is specified. Vblock file servers are computers running a special-purpose operating system. They provide the hierarchical structure for directories and files, and they are responsible for managing access to data, which is determined by the permissions established by the data owner. Each Vblock system can also have a number of disk array enclosures, or DAEs, that contain disk drives. As you learned earlier, a Vblock with multiple DAEs can contain from tens up to thousands of storage drives. The DAE provides power to the drives, and it passes data from the drives to the storage processors. Storage processor enclosures, or SPEs, house storage processors and are typically found in higher-end storage products. In Vblock systems, storage processor enclosures contain two storage processors. But as you'll learn later, not all Vblock systems contain an SPE. Disk processor enclosures, or DPEs, contain storage drives and two storage processors. Vblock systems that use DPEs will contain only one, and not all Vblock systems have a DPE. However, every Vblock system will contain either a DPE or an SPE. Each Vblock system also has a vault. The vault is a number of storage drives used to ensure that data in the storage processor's cache is not lost during a power outage. Recall that cache is a staging area where all data coming into the storage is saved quickly to enhance performance. Data is stored here until it is safely saved to storage drives. Also remember that cache uses random access memory, which requires power to retain its contents. When a power outage occurs, standby power supplies provide enough power to each storage processor and to some of the drives to ensure that any data in cache is saved to the vault. This ensures that when the power goes out, no data in cache is lost. All Vblock systems have a vault. The number and location of the drives is array-specific. EMC is a leader in the storage technology industry, and EMC products are at the core of the Vblock system storage technology. The EMC products found in Vblock systems includes the EMC Symmetrix Vmax family, the EMC VNX family, and the EMC VNX-E family. Click on and review the content of each box to the left to learn more about each EMC storage product family used in the Vblock systems. The EMC Symmetrix Vmax family offers high-end storage systems built for the virtualized data center, providing consistent and predictable performance for consolidated workloads. The EMC Symmetrix VMAX family can provide several petabytes of storage utilizing tens to thousands of physical storage drives and can contain 2 to 8 storage processors. Within Vblock systems, they connect to the compute via fiber channel SAN. It provides tiered storage using enterprise flash drives, fiber channel, and SATA storage drives. And for customers that require file-level storage, a NAS gateway with file servers is optional. The EMC VNX storage family is a storage system that delivers a unique combination of flexible and scalable hardware design and advanced software capabilities, meeting the diverse needs of today's data centers. With the VNX, block-level storage is standard as part of the solution. Customers have the ability to add file-level storage and can choose from 2 to 8 file servers as needed. Customers can choose to tier their data onto a combination of enterprise flash drives, SAS drives, and nearline SAS drives as part of their solution. Each VNX model includes fast cache as part of the Vblock system solution. Fast cache supplements the cache memory built into the storage processor with a number of enterprise flash drives to buffer the most actively used data. The VNXE storage arrays found in some Vblock systems support IP-based data transfer only. Storage area networking is not an option. Only SAS and nearline SAS drives will be found in the VNXE arrays in Vblock systems. They support block-level storage using the iSCSI protocol over an Ethernet LAN. Although VNXE is the lowest capacity storage system found in Vblock systems, it still possesses all of the data protection features that an enterprise requires.
So far in this section, you've learned about basic storage components and concepts, and a little about the EMC storage products used in a Vblock system. Now we're going to talk about connectivity of those storage components to the rest of the Vblock system.
Let's take a moment and review the connections between the components in a Vblock with a unified storage configuration. Starting with the servers, the compute connects through the fabric interconnects to the SAN switches. The SAN switches connect to the storage processors, which connect to the DAEs, which connect to the storage drives. For file-level storage, the storage processors connect directly to the X-blades, which then connect to the LAN switches. Remember that in a block-level only storage configuration, file-level storage is not present. Therefore, there is no need for file servers. In a block-level only configuration, there are no data movers. Now recall that in a unified storage or block-level only configuration, that the unified networking is also an option. For this, the SAN switches and the IP switches are replaced with a unified network switch, which performs both SAN and LAN network switching. One last configuration is for the lower capacity Vblock system models that replace blade servers with rack mount servers. Here, the compute does not use a blade chassis nor fabric interconnects. Instead, the rack mount servers are connected directly to the network switches, which communicate directly with the storage processors.
This is a learning check that provides an opportunity for you to assess your progress. Each question provides feedback to help you remember the content, and a score is provided at the end so you can assess how you are doing. This is not a test and is not part of the certification assessment. Learning check scores are not retained in your records. However, completing these learning checks is great preparation for the certification assessment that comes later. You may take this learning check as many times as you want. Click Next to get started.
Now you've completed the introduction to Vblock system storage. Let's take a moment to summarize what you've learned. First, you learned about the function of the storage and the role that it plays in the Vblock system. Second, you learned about some of the characteristics of both file level and block level storage. And then you learned about the components and connectivity of the Vblock system storage. Next, you'll learn the basics of the Vblock system virtualization.